Thanks everybody for coming back. I hope you had a great lunch. So we now have this very cool discussion session. So this is after all Breakthrough Discuss. And we're gonna kick off with asking you some questions. So we have a fun little interactive poll, some questions contributed by a few of us. And so if you scan that QR code, I see a lot of people are already in with cute little animal faces. So if you scan the QR code, or if you go onto Kahoot, you can put in the PIN. And let's see, we've got about 45 people on. So let's give it one more second. Okay, Dylan, I think we can go to the first question if the instructions stay on the slides. No, they don't. Okay. All right, we're going to go for it anyway with whoever we've got online. All right, so the first question, if AI or ET is discovered, is it going to be running Linux, Windows, Apple, or Android? Let's see what the votes come in. Oh, there we go. If you missed it, the instructions are at the bottom. So if you go to Kahoot, kahoot.it, you can put in the PIN and instructions at the bottom. We've already got 55 answers. I use Linux, by the way. All you Apple users. I don't know if that makes me an alien. Probably makes me an anomaly. None of the above. Yeah, I mean, probably. I mean, we can barely get our own systems to talk to each other. Imagine trying to talk to aliens. Okay. Can we skip to the reveal of the answers? Or we just wait 5 seconds? Let's see. Dun-dun-dun. Ah!
Linux.
Are you saying I'm an alien?
That's not true.
Brilliant. Okay, here's the next question, slightly more serious. Is artificial general intelligence possible? So if you don't know what this term means, it means an AI that is as intelligent or more intelligent than a human. And I've specifically made this not a nuanced question. You have to either say yes or no. I mean, hint, it is probably a bit more nuanced than yes or no. Is there some fundamental reason that it would be impossible to have truly genuine, general intelligence that's artificial? "15 more seconds. We've got, I think everybody's answered, so we could, I don't know if we can skip. It's, okay. 4, 3, 2, 1, let's see. Interesting. Pretty divided. Most people say yes, but a very substantial fraction say no. We could never have truth. That's probably mostly people who've interacted a lot with ChatGPT. Tried to get it to write code for them. All right, last question. When we detect the very first technosignature, will its origin be artificial or biological?
What does that mean?
What I mean is, will we be talking to biological organisms like ourselves, or will we be talking to an entire race of intelligent robots that have superseded their biological origins? If you answered no to the first question, I'm pretty sure you can't put artificial in this one. Okay, 15 more seconds. I think everybody has probably answered. After this, I'm going to ask some of the panelists what they think. Wow, that's quite a split. 50-50. Very interesting. Okay, that's the end of our audience quiz. Thank you all very much for participating. I'm going to open the discussion by asking our panelists whether they think the first technosignature will be biological or artificial. Yeah, thanks, Dylan. We can take it off if possible. And I think leading on to this, is artificial general intelligence possible? And I think the first person I'm going to ask their opinion is Guillermo. What do you think?
Okay, so first, thinking about the signature that we're going to get out from space, if it's going to be artificial or biological. First, I don't think I mean, it could be artificial, but not necessarily general artificial intelligence, in the sense that to have something like general artificial intelligence, we're assuming that there's something like a human in another planet, right? And that general artificial intelligence should be able to do everything that we as humans do, right? So maybe it's more into your field, but maybe we can have other type of life that it's not similar to humans. Can that be possible?
Yeah, what do you think, Vishal?
So I think if you ask me this question the other way, like whether we will detect biosignature first or technosignature, I think this can be answered in a slightly better way. I feel that we will detect technosignature first for following reasons. First of all, technosignatures are going to be longer lasting than biosignature. They are going to be much more common, and they're going to be much more spread out than biosignature. Biosignature will be limited to a planet, while technosignature don't necessarily need to be sort of associated with a planet. It could be anywhere. So extending on that, if you ask this question whether the technosignature we will detect will have origin from biology or from artificial intelligence, I would have to go with the artificial intelligence.
Interesting. Anyone else have any thoughts on it? Yeah, go ahead, Paul.
Maybe, since we're choosing which question to answer, I'm going to answer the question around the general intelligence. And it seems that human intelligence is such a multifaceted, multi-kind of featured thing. And if we were plotting human intelligence from all those different facets that are, encompassed by human intelligence, it would be quite a complicated, multidimensional map. So it definitely feels possible that general intelligence, computer general intelligence, could fit in somewhere within that map.
Is there anyone on the panel who fundamentally believes it's impossible to develop artificial general intelligence? All right, there we have it. Problem solved.
But that doesn't mean that we all agree that it's possible to create it.
Okay.
I think these are the questions for the computer science people. They may be able to answer this in a better way.
Yeah. Yeah, I mean, you have to ask yourself, if there is a fundamental reason why this is impossible, why? What is it about the human brain that could not possibly be replicated? I think it doesn't necessarily mean the direction we're currently going with AI is necessarily going to lead to AGI. Maybe we need something very different. But personally, I don't think there's a reason that it would be, there's no way we could replicate a brain or some more advanced version of it. Okay. Let me ground us back into maybe a slightly more familiar territory as scientists. Most of our machine learning methodology is developed in industry, but there are certain aspects of that are pretty unique to astronomy or other types of sciences. Specifically, we have to deal with low signal to noise, and we have to deal with uncertainties, which are maybe not necessarily problems that industry faces canonically in developing machine learning algorithms. So what should we be doing to adapt our machine learning algorithms to handle these? And I'd like to punt this one to Ashley.
I guess can I clarify the question? Is the question, how do you think we should best think about this uncertain?
Yeah, what needs to be adapted from kind of the standard, if anything, from standard machine learning algorithms for the types of data that we have to deal with, which are generally noisy. We often worry about uncertainties and need to quantify uncertainties.
Yeah, definitely. I think I'm going to not really answer your question, but I will say some thoughts that are really.
That is your right.
The first is that I think one thing, so culturally speaking, in astronomy, we live in what we call this Bayesian world, which is just to say, like, we actually try to quantify our prior information, our scientific knowledge, and our physical laws into what we're doing. And behind the scenes, like, we do that across every subdomain of astrophysics, and that has been true in machine learning, or it's moving towards that in machine learning. We very much would like to quantify this notion of, is this a calibrated statistic coming out? I said this is an anomaly with some like weird metric I've measured. What does that actually mean? How do I know whether or not I need to spend my time on it tonight? And a way to think about that is, what's the probability I can find something exciting? That's really, really difficult, and it actually doesn't quite mesh well with this very Bayesian framework that we've set up, and it also doesn't mesh well with typically out-of-the-box algorithms. Don't account for these types of uncertainties because they're not so important when you're in this really data-rich environment. And all that being said, too, I brought up Bayesian because we explicitly, like I said, put in our biases, our known physics. That's something we want as astronomers. If you're looking for the unknown unknowns, sometimes that's not what you want. You might actually be preventing yourself from finding this by incorporating those uncertainties. The last thing I maybe want to just mention is where it also does become important for us, but then has much larger implications, is because we're doing anomaly detection, we actually care a lot about like the tail ends of distributions. And that is exactly where these algorithms fail. There's many really upsetting examples of this across the board where you try to get information from an algorithm and you end up basically getting out the mean of that algorithm. A really like famous example from quite a few years ago is reconstructing faces and putting in a picture of someone who's clearly Obama and then getting out a picture who's clearly a white man. And like, you know, that has a lot of implications. For us, mathematically, and looking for new phenomena, the implication is just that we often default to the first order moment, or like the mean of our distribution. That's not what we want in this case. And so there's a lot we have to think very carefully about as domain scientists.
Oh, thanks, Ashley. Dan, do you have any thoughts on this? I know you've thought quite a lot about these sorts of topics.
I think as scientists, if you want to build trust in your models, you have to have really good uncertainties. You know, people won't believe your models. If you don't have reliable, robust uncertainties at the end of it, then that feels almost unscientific. And so I think this is particularly true for science models, which is very different to the problems that you face in industry, where when you take a picture of a cat, you don't really care about the uncertainty of every pixel in that cat. But when you take a picture of a galaxy, you certainly do. Or you have a spectrum, you certainly do care about the uncertainties of each of these things. And so you want to be able to quantify this, and you want to be able to make sure that those uncertainties are robust and can be flowed down to downstream tasks. And so having a distribution that represents every prediction, I think is really, really important. But then you've got the trap of if your distribution is, you know, you assume it to be Gaussian, and it's not Gaussian, or it's not normal, a bell curve, for those not too familiar with that term, then you'll have the problem that, you know, if you're looking for the tails of the distribution or things that are further out, you might not be able to model those things as well as you might otherwise. So it's a double-edged sword that we need uncertainties for people to trust us, but sometimes those uncertainties and those distributions aren't well described.
We don't want to overspecify the model. A kind of follow-on question from this is, are there any other aspects or problems that are unique in astronomy or related fields compared to other fields that use AI? Guillermo, if you want to go.
So following up on the previous question and related to this one, I think that one thing that happens in astronomy is that we don't get access to the real thing, to the ground truth. For example, if I'm classifying between cats and dogs, I can grab a dog and pet him or whatever. I know this is a dog, right? I can sequence its gene. I can do stuff, right? In astronomy, the things are too far away, right? So I won't be able to get access to the thing, to the object of study. I cannot get access to the galaxy itself, to the star itself. And that means that all the models that we create are biased because of that, because we don't have the ground truth. I remember in a paper we wrote a couple of years ago, we found a spheroid galaxy, an elliptical galaxy, that it was kind of weird, but we looked at the data from SDSS, and it was clearly as a spheroid galaxy. But then we got to HST, and we could see the spiral arms, right? So because of the quality of the data, we weren't, as humans, being able to classify it correctly. And this was, we found it in Galaxy Zoo, and 100% of the people said this was an elliptical galaxy. Everyone said it.
Interesting. Does anyone else have thoughts to add? Problems that astronomy faces that are quite unique? Paul, do you have some ideas?
I really like that point, Guillermo. And I was going to say that at a cosmology level, it's even worse, the situation, because there's only one universe. So we're reliant on the data, observations of that single universe, and a whole bunch of simulations, essentially. So yeah, I can completely agree with you.
So a follow-on question, especially talking about uncertainties. There's a famous, of course, Carl Sagan quote that extraordinary claims require extraordinary evidence. I wonder how many times people in the SETI community hear this quote. But it's true. And more broadly, not just the detection of a technosignature, which would require an extraordinary amount of evidence, but just in anomaly detection, when we actually make these kinds of discoveries, naturally scientists are skeptical. So what kind of evidence would it take to convince the community that we have actually detected a technosignature, or very similarly, we've detected some completely new class of object? How do we actually support our claims made by, when these discoveries are made by machine learning? Let me start with Vishal.
Yeah, so in the technosignature community, although it's a bit controversial, but they have devised a metric called a Rio scale. Now, Rio scale is a sort of a quantifying way of identifying or putting quantity on any detection that you make. And there are various uncertainty in there, obviously, because you don't know a lot about your detection, and those factors really can put your Rio scale from anywhere from, so the Rio scale goes from like 0 to 10. 0 means it's totally uninteresting, 10 means that a UFO landing on like a White House lawn. You can think of that way, right? It's like a direct evidence that you can verify. It's up to that level. So it has a long range, right? So when we make when we potentially will make a technosignature detection, it will be somewhere in the middle, obviously. So in order to quantify that, it's going to be very challenging. I can tell you example from like radio technosignature searches. It's a long process that will happen if we ever make a detection. It needs to be followed up by multiple observatories. Signal needs to be present all the time. If it's intermittent, like a transient, then we will have no way of verifying. Like, for example, like wow signal. Wow signal was just detected once, although we detect similar signals all the time, but it never seemed to repeat, right? So we have no way of verifying it. So there are certain criteria. This is an example, but like certain criteria that it needs to sort of go through in order for us to say with confidence that it is real.
Anyone have something to add? Dan, do you have thoughts?
I think I think Madhu might be more familiar with this, but it's in the biosignature, when you do detect a telltale signal of a chemical, it's hard to get people to trust you that this is the smoking gun, right? Even if there is no other way you know that this is produced on Earth other than artificially, it might not be enough. And this is why I feel technosignatures might be a better approach, because as long as you get some repeating signal that, if an alien started shooting Morse code at us, I feel like that would be that'd be a pretty good smoking gun.
If an alien started saying, hey, we use Linux, that would be pretty good, pretty strong evidence. All right. Any other thoughts on that? I definitely have other questions, but I feel like this might be a good moment to open up to the floor and just allow any questions from the audience, either for specific speakers, in which case maybe direct your question, or to the entire panel. And I think we're going to throw cubes at you. So, you might want to duck. Thanks, Ron. Any questions? All right, who's got the first question? Let's do the one in front. Yeah.
Cash the box. My question is for Paul. Since I was surprised by the manifold approach, as an observer, so someone who tries to have the best possible data, the spectrum taken in matrix in order to have the best possible quality of the data. I was surprised when you said that you have somehow to downgrade the data to do the manifold, to select outliers and whatever. And so I wonder why we do such an effort, technological, data analysis, whatever, to get multidimensional data that if they are not used or useful.
So that's a great question. And maybe there was a point that I didn't stress highly enough, maybe towards the beginning of the talk, that one of the things, I guess, that's driving this sort of approach is the sheer volume of data we've got. So it's an oft-used phrase, we're living in a golden age of astronomical spectra and astronomical data. But I've got a lot of collaborators within DESI who are perhaps, say, experts in tidal disruption events. I think those were mentioned a couple of times, or quasars, broadline quasars, who go through and they actually look at each and every spectrum. And they, as you say, I mean, that's the kind of the ideal, that you've got time to look at each spectrum. You've got your full, the full sort of experience that you've got as an astronomer in that subject matter area. And so you're not losing any information, you're looking at all the data. The problem comes when, as I say, we've got 40 million spectra in DESI, and then we're going to have orders of magnitude more than that in some of the other observation types that we've got. And there, you simply can't use visual inspection for that whole data set. And so you've got to have some way of getting to what you think will be, and curating what you think will be an interesting subset, and then eventually getting a human in the loop, doing some visual inspection on that. So that's what some of these dimensionality reduction techniques try and do, some of the unsupervised methods try and do. They try and just give you that set or that short list of data that we think, those are probably good ones to look at. But what people then look at is they look at the full, they'll look at the full spectrum. And then, with techniques like astronomy, which are so good at then curating those maybe 1,000 spectra that you've got, if you tell it that you're really interested in black holes or tidal disruption events, it will try and you show it what those look like, it will say, okay, and so why don't you particularly focus on these top 50? So your point is really, really well made. If you had all the time in the world with lots and lots of people, yeah, you'd look at the data in its full glory.
Thanks for the great answer, Paul. Next question. There's one over there. Just before you ask it, hang on. The question after this, I would love to come from a student or postdoc. So young people in the room start thinking of questions. Go ahead.
Okay. Yeah, so we heard a lot about anomaly detection, but not a lot about exoplanets. With exoplanets, our problem is not so much excessive masses of data, but we have a time series for each planet. We have a time series of spectra combined from the star and the planet, and we're trying to infer from that fairly high dimensional structure, the 2D, 3D, and maybe even 3D chemical composition and temperature structure. The workhorse for a long time has been Monte Carlo Markov chain and Bayesian inference, but I have to believe that modern machine learning techniques could help our retrieval, and I was wondering if there are any thoughts about how machine learning could help us get beyond Monte Carlo Markov chain.
Great question. Anyone want to tackle exoplanets?
From the technosignature side of things, I can mention that if you want to look for anomalies in exoplanet searches, there is also a case for technosignature For example, incomplete Dyson sphere are a good example of producing anomalous light curves. This has been observed. I mean, we have one case where we thought it is a megastructure like the Tabby star. And similar searches are ongoing. There are a couple of papers where people have actually used anomaly detection techniques in order to look at all the light curves of TESS data, all the light curves of the Kepler data. And they have in fact trained the model based on completely non-spherical objects passing in front of the star. So what kind of light curve, what kind of dips those objects will create, and you can train a model from that as well. So yes, that work is sort of ongoing for TechnoSignet side of thing.
Dan, do you want to say something?
Yeah. So I mean, back to the question of whether MCMC, the Markov chain Monte Carlo, is there anything after that? One problem with these retrieval methods is that it's highly dependent on the chemicals that you input at the start. So you have to predefine what chemicals you believe are in the spectrum, and then your MCMC will go through and search that parameter space. And so it feels like, you know, if there was a technosignature there, or if there was some other chemical or some sort of unknown phenomena going on, it would be much harder to find that using standard approaches. And so we have a lot of machine learning techniques, such as simulation-based inference, that can search a lot larger parameter space a lot faster, and it might enable you to actually input various different parameters in there, or various different molecules in there that can search this at least a lot faster. And the benefit of being faster is that you can search a wider parameter space.
Thanks, Anne. Okay, where's my question from a junior person? Got one there. Oh, got lots, great.
How do we navigate situations where one research field's desire to apply AI to their work might hamper the goals of other fields? As an example of this, it seems that in order to improve multimodal foundation models in geospatial intelligence, we may need larger amounts of higher quality data, which might involve launching more satellites into space. However, as we heard from Vishal, this could lead to more radio interference, which could make it more challenging to search for techno-signatures using AI.
If you want to make an astronomer cry, remind us about all the satellite constellations that we have to figure out how to deal with. Great question. Who wants to tackle this? Everyone's like, nope, not me. Ashley, what are your thoughts?
Okay. Sorry. No, I mean, I think it's really challenging. It's a deep philosophical question. A different way of saying this is a lot of these very large models, honestly not astronomy, we're not the big offender here, but they take up a lot of energy. And what cost is that to us? I don't know. It's challenging to say, and it really isn't a great answer. There's no one decision of what is the most worthwhile scientific question out there to be asking.
Anyone want to add? You look like you want to add something.
Well, again, brilliant question. That was a very good answer, I thought. I guess as these issues become more in the mainstream, and as you say, especially in terms of the resource, or the consumption in lots of different ways of these different models and these different fields becomes more important, then I guess naturally, like it or not, they'll probably be of more interest to maybe governmental organizations who tend to dictate and how priorities and resources are balanced against each other. So,
I agree with that. I definitely think that there can be an issue of policymakers not necessarily talking to each other. So satellites are a good example. The US government and countries around the world are putting in something like $1 billion into the Vera C. Rubin Observatory, and many science cases are very heavily impacted by the satellites that are also allowed to launch by the same organization. So there is definitely a level of policy that discussions that maybe aren't happening. Great. Okay, where's my next question? There we go.
So for everybody who's not neck deep in AI at the moment, you'd be forgiven for thinking that after the discussions here, that there's a lot of time series models out there. And I see some smiles up there because, there are not. Really, when you're talking about foundation models, there's large language models, we have large video models, we have large audio models. So maybe, Alexis, this might be a question for you as well, is where are the large time series models? Are they coming? Are people working on them? And then finally, for those of you who are in the research community, Are you actively collaborating on creating some of these models? At MIT, obviously, you've put one together as a kind of a foundation model. So are you looking to expand that, involve other people to collaborate, create, I would say not sell, because you're all in the open source community. But is there any talk about doing that so that we can actually advance time series foundation models?
Great question. Alexis, do you want to comment on why there aren't any time series foundation models? Do you want to grab?
Hello. Yeah, it's a good question. I guess the one thing in terms of time series that comes to mind to me is audio. People are actively working a lot on very large models for audio understanding, generation, music generation. So these things are happening. So in terms of open source, like I'm not sure. What I can tell you, like me personally, for the work around sustainability and these models, we do hope, and a lot of these models are open source. So for example, the largest weather model, GraphCast, is open source. So specifically things around sustainability conservation, at least for Google, and I think a lot of other, like Meta and stuff, they do try to open source these models. But it's still hard to, even if you open source the model, it may be very difficult for somebody else to reproduce those results. It's very expensive to do that.
Does anyone want to comment? Yeah, Ashley, you want to? Collaborating on foundation models as well.
Oh, no. I don't believe in time series foundation models.
You don't, wow, a controversial statement. Right, let's go. Why don't you believe in time series foundation models?
I think time series are particularly challenging in a way that images truly aren't. I think audio is a good example of like, yeah, that's fair. There's a sense in which, oh, so sorry. There's a sense to me in which audio, very similar to images, it's almost like conditioned or has this very strong prior in its structure. The way I'm speaking has a very cadence that you're used to. I don't do things like suddenly have chaotic behavior, and I mean that mathematically chaotic. I'm not coming from a stochastic process. And that's true in time series. There's so much interesting behavior. And then in the Astro world, it's multivariate, meaning there's different signals coming in, but the signals are correlated with each other. And also they're not coming in at an even time. I get them randomly. There's so much more going on to me than in images. And so that's why partially I think we're so far off from a foundational time series model that I don't believe in it right now. I think it's not the direction to be thinking about.
Okay, who wants to fight back on that? Everyone, everyone! Go ahead, Guillermo.
Okay, so I kind of agree, but not completely. All right?
No, you're supposed to have a fight.
So you're right. If you think about a time series foundation model, like a general time series foundation model, it's going to be really hard, but you can still build it, right? I mean, if you had the data and you want your model to follow the distribution of the data, then you may get it, which is what we do with language, right? We're following the distribution of the data that comes into the model. In the case of astronomy, we built a foundation model, which is Astromer, but it's limited, again, to the distribution of the data that was built on, right? So that means that, for example, if you switch the cadence, the model changes completely, right? So then you have to think about how you encode the time into the time series model. And that makes a huge difference, right? And, but again, once you switch that, even if you do that, the model will still follow the data, the distribution of the data you're feeding into it. But if we grab all the data from all the time series that we have in the world, we could build a time series model, right?
But that exists, and it's very bad. Like TimeGPT exists, and it's really bad. Gaussian processes can easily outperform a lot of their baseline metrics.
Right, but that's because the distribution is too complex, right?
Yes.
Right, but if, sorry, I was thinking about light curves, sorry.
Okay, that's fair.
Yeah. So in terms of light curves, I think it's not that complex.
But what makes foundation models really good is massive compute. And I don't know if there's many companies out there, even DeepMind or OpenAI, who are putting that much effort into massive compute for time series data. And the ones that probably are would be the hedge funds. But we don't know what's going on inside there. Maybe you do.
I don't know.
He's like, I'm out of that world.
And so I don't think it's impossible. I think it's just we haven't put enough effort into it. And I think astronomical time series are particularly challenging because we have a lot of missing data gaps. We have multi-channels that are partial observations in each of them. So it's a much tougher problem for our data set. But things like audio, yes, they're stochastic, but they do have or like stock marks, they do have long duration trends. And if you go to the right frequency, the right range, then yeah, you totally get trends. On short timescales, for sure, but that's also true with images.
Yeah, but I mean, I think to follow on with Ashley's point, that one of the complexities of this problem is the sheer range of timescales we're interested in that something could be anomalous on, right? It's everything from milliseconds to years. And that is not really an issue we have with images, right? We don't have fractal images where you can be interested in these 2 pixels as well as the whole thing. There is hierarchy, but it's nowhere near the level with time series. So it is a very challenging problem.
But does it always have to be one-dimensional? When you are, for example, looking at the time series data, there are other metric or other streams of data that you can also correlate with that and try and make your prediction better. Supposed to kind of do it that way.
You're talking about like combining image data and spectra. Yeah, these are the multimodal kind of foundation models.
Data as well, like, yeah.
When that's available, which is not often. Great question. Sparked a lot of discussion. Next question, yes.
My question is for Guillermo. You introduce alerts as a very flexible system, and I remember your slide about the classification of AGN, pulsars, something like that. My question is about, because we have more than 10,000 unclassified exoplanets. Well, the question is, could your alerts used to try to classify exoplanet, because usually we have 3, maximum 4 parameters, no more, excluding the black dot of the planet, of course. Could your system be useful for such research or not?
So I would say the system as is right now, it's not built for that, all right? But all the techniques behind the system itself, they can be applied to planets or to whatever data stream you have. At some point, we talked in the team about building a version of Alersi for planets, for exoplanets. But we decided not to follow that route because it was a lot of work, right, to build the whole system. Now, the algorithms are not that hard to build, but the problem that's really challenging is starting from the algorithm that you created for the paper, putting that into production so that it works on a real alert stream. That's a lot of work. That's a lot of work. It usually takes us around 3 months since we get the model, between 3 and 6 months since we get the model until we put it into production and we do all the sanity checks on what the system is doing. So building a system for something different, like the whole system, would be really challenging. Building the model should not be that hard.
Okay.
Michelle, let's just do one more.
I think we're actually going to have to close the panel.
Okay.
I'm sorry, everybody. We're actually already eating into coffee time. But I want to ask one final question of our panel before we close, which is basically, what is the future? What are the techniques that you're the most excited about? Where is the field going? I'm not going to ask each and every one of you. I'm going to ask the one who looks the most excited to answer the question, which is, I don't know, who's the most excited? I think it looks like Paul.
Oh, okay. I was trying not to catch your eye, actually. My approximation, my first approximation to excitement. Where's it going? Well, I think maybe looping back to the first question, or one of the first things we talked about in terms of general intelligence. There's so much that we've seen in astronomy, I guess, from everybody's interest in ChatGPT and large language models. Even if we're not necessarily specifically using large language models in astronomy, we're using a lot of the tech from it. So the attention mechanism and transformers and so on are being used in it. So I guess I guess that's the way things seem to be going, to try and push towards general intelligence, whether it, is possible or not. I mean, I guess we think it is, but well, whatever. But so I reckon there'll probably be a lot of collateral developments that will come from that we will be using. Again, whether we're using general intelligence or not specifically, I reckon there'll be a lot of spin-offs that we will be using in our day-to-day work.
That's great. Anyone else have something to add? Michelle, what are your thoughts?
I mean, I can't really comment much about how the AI is going to, what new techniques are going to come in AI, but I can comment from this side of techno-signature field. And I can say that it's sort of mind-boggling the way we are able to conduct the searches right now and what future holds for us in the next 5 to 10 years. The new facility is going to generate data. I mean, you talk about terabytes a night. We are already generating several hundreds of terabytes in an hour, in fact, at radio facilities, right? So that's an enormous amount of data that comes in. And we definitely need something that can work in real time to make inferences and basically allow us to do this processing much more faster. Because we talked about this Bayesian approach, right? We don't know the probability of life. We don't know whether the evidence we will get will suggest there is life. But the middle probability in the Bayesian thing is that how well you understand your experiment so that anytime you make a detection, you can say with certainty whether that detection is real or not. And that will depend on making more observations by collecting more data, and that is only possible through AI.
So AI meets giant surveys, and it's never been a better time to start looking for techno-signatures. So with that, I'd like to thank all of our speakers again for a very interesting panel. And thank you very much to the audience for all of your participation, and please enjoy our 20-minute coffee break.